Hi, I'm Haegin from Hanyang University, South Korea. I'm very glad to give my presentation in this workshop. The topic of my presentation today is motion capture data-driven, phantom animation, and 4D Monte Carlo dose calculation. In the field of radiation protection these days, individualized dose assessment is being more and more important, and in line with this demand, many studies are now being conducted to individualize human phantoms. The first step of the phantom individualization was to construct phantoms in various body shapes and postures and investigate their dosimetric impact. And many research teams, including us, have revealed that different body shape or posture can actually significantly affect radiation doses. So now, as we know that the body shape or posture can matter, now the next step would be individualizing phantoms with a certain body shape and posture. The phantom individualization can be done by adjusting template or model phantom to personal body sizes and the actual motion data that can be obtained from various motion capture devices such as suture sensors or depth camera. And our framework to individualize the phantoms by considering both of these data is to first deform the phantom by adjusting its dimensions to personal data like 3D scan data, and then animate this phantom to follow the motion of the individual. So this is the goal of our study, and for now we are working on phantom personalization in here and phantom animation separately. And today, as the title of my presentation, I'll focus on motion capture driven phantom animation. So when you think about phantom animation, the very first question may be which phantom to use. Our answer for this is the adult MRSPIS, which was introduced in the first presentation of this session. To be more specific, we chose to use tetrahedral mesh phantoms. There were several reasons for this. The first one is obviously its high deformability. As the tetrahedral mesh is not rigid structure like voxels, it can be rather freely deformed. The second reason is its capability to define even very small or thin radiosensitive regions, including islands or skin base of the layer, which can be really important for external exposures. In addition, despite its such high complexity, it shows fairly high computation speed, as shown in Dr. Furuda's presentation. The next two reasons are about the characteristic of the tetrahedral mesh, that it is volume mesh. So firstly, as tetrahedral mesh is a volume mesh, it consists of a number of tetrahedra with confined volumes so that local density can be easily manipulated. This is very advantageous in phantom animation technique because as the phantom changes its posture, local volumes can vary. Some of them can extend it and some of them can be compressed. And this issue can be compensated if the local densities here can be accordingly adjusted. Finally, we can calculate the dose distributions for the reference posture and accumulate the doses to each part of the body even when the phantoms are in different postures. This means that even the phantom is in different postures like here and here, we know that the dose to hand is dose to hand. So now let's move on to the phantom animation technique. These two are the main requirements of the phantom animation technique considered in the present study. Firstly, of course, it should be applicable to tetrahedral mesh phantoms. And second, it should be fully automated and should be very fast because phantom animation is actually a series of work to construct posture deformed phantoms for each of the frame. And if the technique requires manual project or slow, it may take forever. So the technique we have used for the phantom animation is BBW DQS deformation methodology. As also can be easily recognized in its name, this methodology consists of two steps. One is BBW here, which is pre-processing, also called as rigging in the field of computer animation, and the another one is the QS here, which deforms the phantom for each frame. Actually, these terminologies here, like rigging, skinning, BBW, DQS, may be unfamiliar to some of you, but these are actually pretty popular concepts in 3D animations. In next few slides, I will give you very brief technical explanations about these. So first, let's start with the rigging process. So firstly, what are the rigging and what are the weights? So the rigging is a procedure to compute weights as written in here. And the weight here represents how a certain vertex should move as a function of bone rotations. So for example, for the bone in here in red one, the weight of the yellow vertices would be 1, and dark purple here would be 0, and green part here in this area would be 0.5. This means that if the bone in here moves, the yellow vertices would 100% follow this bone, and purple one would not move, and green ones would 50% follow this bone. So, rigging process is basically very typical pre-processing required for general 3D animations. However, the thing is that in conventional methods, this rigging process should be done manually by professionals by using painting tools, which is very unfavorable for us. So what we adopted is BBW technique, which can do this automatically. As written in here in second bullet, BBW is a constraint optimization problem to enforce smoothness, which seems a bit complicated, but the concept is pretty simple. So if we provide skeleton structure like this green line here, this works as the constraint with the weight of 1. Then the program spreads the weight to neighbor vertices so that the vertices can automatically colored as shown in this picture. However, there was one issue in here. BBW or rigging process is usually for surface models, so it is not suitable for complicated tetrahedral mesh phantoms. In my case, I could not calculate weight for a marsupial with its all internal organs because of the lack of computer memory, although it was 64 gigabytes. To address this problem, we developed a dedicated methodology to use it for tetrahedral mesh phantoms. And for this, firstly, we constructed a shell phantom that can cover the whole phantom. Please note that the shell phantom is empty without the organs, so it is just hollow phantom. Then we calculated the weight for this hollow phantom. What we did next was to use this weight information of the hollow phantom to calculate the weight of the vertices for the whole tetrahedral mesh phantom. In here, I would not go so deeply, but I can say that I used tetrahedral interpolations for this. So in this way, weight could be calculated for the whole complicated phantom, and these pictures in right side shows the weight finally calculated. It can be seen that the weights were well given for both skin and internal organs. So we have just finished the pre-processing part in here, and now let's move on to the on-processing here called skinning or DQS. So the next, what is skinning? Skinning is the process to compute the new position of a vertex moved according to the bone rotations. And a very simple and straightforward method for this is linear band skinning, which is also called as LBS, which uses weighted summation of the bone rotations as written in this equation. This LBS is very simple but has critical problems, including joint collapse. In joint area here, you can see that there is overlapping issue in this part. Such intersections should be minimized because they can cause problems during the particle transportations in Monte Carlo codes. Therefore, instead of using the simple LBS method, we adopted DQS, which as you can see in here, causes much less intersection issues. Plus, when it is applied to human model, its posture can be deformed in more natural appearance. In addition, because the QS is still simple weighted summation, it still shows pretty good computational performance. So this was the technical explanation so far, and now is more interesting part. Strengths of BBS DQS. The first one is that it can deform the phantom very realistically. So this slide shows the phantoms that was deformed according to the real motion capture data. You can see that the outer skin is very natural and the internal organs are also very naturally deformed. And this picture shows the close look of the internal organs in stomach area. You can see that although it's pretty complex structure, it is all well deformed, and even in joint area here, the vessels were naturally deformed according to the bone movements. And this picture here shows the backbone of the phantom, and you can see that the backbone here were all very naturally deformed. The second strength of BBW DQS is that it can reflect motion capture data as it is. This picture here shows the skeleton structure of our motion capture device. As can be seen here, there are several joints in torso region. Compared to limb joints, these joints are more difficult to reflect in posterior deformations because unlike limbs, nose and torso can be affected by more than two joints. Therefore, in many simplified posterior deformation methodologies, these torso joints are ignored, assuming that there are only slight deformations in these torso joints. However, in BBW DQS, all the joints are considered as given in motion capture data. This slide compares how it can be different when torso joints are ignored. Although it seems like there is no dynamic deformations in torso area, you can still see apparent differences between them. Also, when torso joints are ignored, I think it looks a bit awkward. Another possible issue that can be raised here is that the position of islands can be very different from where it should be. In here, where all the joints were considered, the phantom is totally looking at the right side, but in here, it does not. The third is computation performance that I have slightly mentioned in previous slide. So again, these are the two steps of the BBW DQS deformation. Our strategy here is that if we need a lot of computation resources for realistic deformations, let's do it in here in pre-processing and keep here very simple and fast. Compare these two steps. The most important difference between two is that the calculation of BBW is constrained optimization problem that requires several iterations, while DQS can be done by simple weighted summation. Because of this, as can be seen here, the pre-processing requires more computation resources, while on-time processing requires only a few of them. Still, however, the compute resources required for the pre-processing is not that much. In addition, Pre-processing is just a pre-processing, and it is required only once for each phantom and each motion capture device, which means that we need to do this only once when we change phantom or device. In addition, as we aimed, it is fully automated system. This is the overall procedure of the phantom animation by BBW DQS. And here, these two are done by dedicated C++ programs developed in our lab, and the only manual process is this part, assignment of joint positions and set up the skeleton structure. If phantom changes only, the joint positions need to be reassigned, and if the motion capture device changes and the whole skeleton structure may change, and it should be reset up. Both of these are very simple and easy work that can be done in at most 30 minutes. So, as I did in this slide, the phantom animation can be easily applied for different phantoms with very simple pre-processing. This also means that the system developed in the present study can be easily applied to any motion capture device. These two are the motion capture devices being used in our lab. This is the suit with the sensor, and this one here is the depth camera that does not require any sensor or devices on the actor's body. Although these two devices look so different, once we have the skeleton structure like this, it can be easily used for BBW DQS system with the one simple pre-processing. For the Monte Carlo dose calculation, a dedicated Gen 4 program was developed by implanting DQS Phantom animation program in it. In this program, after the initialization, this loop here was repeated, and it deforms the phantoms for each frame and update the Gen 4 geometry. Finally, this is how it looks in Gen 4 visualized UI. And this small image shows the actor with motion capture devices and the motion data obtained from it. You can see that all three are well synchronized. There would be numerous applications where phantom animation techniques can be used, and as one of it, we have conducted a study to assess worker dose for emergency retrieval scenarios for detached entity source. This picture shows the typical structure of the gamma ray source projector. When it is not being used, this source stays in the shield here, and during the entity process, it is projected to the end of the tube. And the projected source sometimes are detached, mainly because of two reasons. One is the disconnection of the pigtail, and the other one is the damage of the tube. The source can be stuck when the tube is damaged. For such situations with detached entity source, there are some general retrieval scenarios suggested by IAEA documents or various workshops. So in the study, as you can see in this table here, we first established 5 representative retrieval scenarios. This looks simple, but we actually went through tens of meetings with experts from regulation body, projector vendor, and entity service company. Today, I'll show you what we have done for application very briefly, so let's just look into the first one closely. Well, I have not prepared the slides for specific procedures for this study, but we have obtained the motion capture data by rehearsing the established scenarios with entity technicians with the motion capture suit on them, and then used for the Monte Carlo dose calculation program to calculate effective dose rate here. This is the result for the first scenario called connect and push, and you can see how those changes for each specific procedure. For the first procedures here, you can see only slight doses. However, in step 4, you can see rather higher radiation doses. It is because the worker moves the unshielded radiation sources by shaking the guide tube with the tongs. So the source moves from the top of the worker to the bottom. The doses then decrease as the source is being shielded. And until the very end of the scenario, the worker receives only a small amount of radiation dose. We have done this for all 5 scenarios, and this graph shows the results altogether. With these data, it is possible to choose emergency scenario that the worker receives the least radiation doses. For example, for disconnect source, fishing cable would be the best option. However, the results show that if the source can be well retrieved by following the planned scenarios, the radiation doses for its retrieval would be very low, considering the annual dose limit 20 millisievert. Now I'll move on to the future works part, which is the plans to further develop this topic. Firstly, we will work on other applications. The application we are currently focusing on is dose monitoring system for interventional radiographic procedures. This shows the dose calculation for treatment called PCD. This one here shows the particle transport in Gen 4, and this shows the skin dose distributions. Red shows the high dose, and blue shows the no dose at all. From this demo program, we could see the feasibility of dose monitoring system. However, the thing is that at this time, we used motion captured suit with sensors, and the quality of motion data was poor because of the magnetic disturbance. Actually, there was MRI device in the next room. So instead of the suit, we are going to use the depth camera. Also, we are going to accelerate the program so that we can use it for real-time dose monitoring. Also, as I mentioned in the introduction part, we are going to incorporate phantom animation technique with phantom personalization technique. This shows how MRCP can be changed to be adjusted to target 3D scan data. After the incorporation, we are going to use the personalized phantom instead of the MRCPs for the animation technique. So this was all for today, and I'm gonna end this presentation with a video clip. Thank you.
오빤 강남스타일 강남스타일 옵옵옵